Bang. Population samples and sampling distributions are what I want to review here. So there's this kind of hard thing to grab, like a cloud population. And we want to know things about a population. And to do that, we take these samples. So a population has these things that are true about it, and those things change over time. Like, the average height of a population might change, the average weight of a population might change, a percentage of women in a population might change, or maybe this is something else. Maybe we're manufacturing screws, and we want all the screws to be 3 inches because we claim it's a 3-inch screw. Well, how do we assure that our machinery is always making 3-inch screws? Those are things that need to be sampled and tested regularly. And there's just tons of possible populations out there that we'll take samples of to test. Now, when we run tests to estimate parameters, like with a confidence interval, or to say, is it still true that we're making 3-inch screws? Is it still true that about 30% of the population is not getting vaccinated? And we make those predictions, we're making this kind of bridge between a population and a sample. That's called a sampling distribution. And remember, distribution is just kind of a graph. It's a whole bunch of data. We might be sampling and calculating a mean. So we might have samples and a mean. So we have this thing called X bar. We're trying to figure out in the population, what is mu in the population. And what a sampling distribution is, it's just many, many samples of the same size. So many samples. Oops. The same size. Like we were looking at many samples of 120 games. What percent did the home team win? Many samples of 31 houses. What was the average price in each of those samples? So population, that's everything out there. A sample, just one collection of data from the population. A sampling distribution is the idea of many samples, and we just graph something like the mean. Graph all sample means. Some things that are going to be true about these 3 different groups is the means are going to be around the same of all 3. So some kind of theoretical facts. Theoretical facts. The means of each of these will be about the same. This idea that the means are about the same comes from an idea in statistics called the central limit theorem. And the central idea right there from the central limit theorem is this idea about the means of each of these being about the same. The limit part of it is as the sample size gets bigger, then the means of these 3 get closer and closer together. And the sample size is like with the houses, I said n was equal to 31. I was looking at 31 houses at a time, right? That's totally different than in StatKey when I run like 7,000 different samples. Every one of those samples right there is size 31. If I point to one of the dots on the screen, you'll see in the side screen here, it's saying, hey, for that group of houses right there were 31 of them. For this group of houses here, there were 31 of them. My sample size is not 7,000. My sample size is always 31 here. What the central limit theorem says is if instead you grab 50 houses or 100 houses, right? It's not this 7,000. That relates to the sampling distribution. We could do more than 7,000. We could do 100,000. Right? That's a whole nother subject. The central limit theorem does not exactly address that. So that sample size refers to my n, which is different than those 7,000 resamples I make. And I've seen in the homework and write-ups, there's some confusion on that, and it does take some getting used to. So we have a population. We usually can't get the whole population, so we try to explore it by taking samples. We take one sample at a time. Maybe it's 50, maybe it's only 6 things in the sample. Maybe there's thousands. Like when I was looking at the quote that about 30% of people in February were saying adults weren't going to get vaccinated, that was from a sample of 10,000 people. One sample, 10,000 people in there. There was an example in the book where a restaurant was concerned about arsenic in chicken. To measure the arsenic in chicken, you have to take a biopsy of the chicken meat and have it analyzed. That is not cheap. And so they were only able to have a sample of size 6, right? Usually with the central limit theorem, we want n to be greater than or equal to 30. Can we get by with less than that? The answer is sometimes. We'll get into that next week. So the next couple of weeks, we're going to explore this idea called the central limit theorem. Central limit theorem is part of the theory about why things are turning out for us the way they are. What do I mean by that? When I looked at the Hermiston home prices and those were real data I grabbed from Zillow in the month of February, 31 houses. When I resampled those 31 houses, so 7,000 times I resampled those 31 prices, I got this graph right here, and this graph right here has this symmetric bell shape to it. Right? So notice the shape of that graph. Strangely, the home team wins, which is nothing like housing prices. It had a symmetric bell shape to it. And so I just want to bring up a couple of other examples we've seen in the past, back at the stat key. And what you may have noticed is that whether we were doing a mean or a confidence interval, that this symmetric bell shape kept popping up. So let's see, restaurant tips was in here. So at a restaurant over a few nights, they recorded tips. So 157 bills were collected, and they would write down what was the tip for each of those bills. This is that sample right here. And so the population would be, I guess, all tips at this restaurant over time. And we run, we resample from that 157 thousands of times. Then we get a whole bunch of new means plotted here. And when I point to one of these dots on the dot plot, it shows a new sample down on the bottom right. Every one of those is 157 tips, resampled from this deck of cards here, 157 cards. And let's just go for the standard 5,000–6,000-ish. And notice the shape I get. It's that symmetric bell shape again. And it doesn't really matter where the data came from, whether it's a mean or a proportion, most of the time we're going to get this shape. And that's another thing that the central limit tells us about. So again, I have this symmetric bell shape here. And I kind of smooth it out. This was restaurant tips. I'm just going to bring up one more for fun here that we'll explore in a moment. Stop sharing for just a sec to show you. I brought up this idea before. Can you kind of see that? There's some glare on there. I went to Bi-Mart again, and I got a can of mixed nuts. And on the label, it says less than 50% peanuts. Right? So I said, oh, really? Okay. I want to double check this. So I counted some of the peanuts, mixed nuts. So here's me putting all the peanuts in a plate. So I kind of took a handful out at a time and separated the
You got to reshare your screen.
Shit, thank you. Good job. Where's that button? There it is. All right, so here's a picture. I'll share the spreadsheet in a minute. I took like a handful out of here at a time. Each handful was how big? 60 to 100 nuts ended up in my fist each time I pulled them out, and I sorted them and counted them. Counting them was a little weird because I had to decide, well, how do you count these? Do you count pieces? So at first I was counting pieces. And then I thought, no, when they say peanuts, they probably mean a whole peanut. So then I tried to, put them together to talk about whole nuts and whole peanuts. I got slightly different results either way. So interesting thing is if I take this whole can as a sample, My sample size was 240. 117, oh, no, sorry, here's the total. 357 whole nuts was my estimate for this can right here. 240 of them were peanuts, which gives me a proportion of 0.672. So I'm using my can as a sample of the population of nuts from this company, where they claim less than 50% peanuts there. And so what I'm going to do in a moment is make a confidence interval with that. And actually, let's just do it right now. So I need these two numbers right there in StatKey. And StatKey did something similar. They had some nuts. Let's see, home team wins, I'll leave that. This is my housing prices, and this one is my restaurant tips. Let's bring up a new screen from StatKey. And I'm going to do a confidence interval for a single proportion. Now, this is somebody, one of the authors of the book, went out and grabbed some mixed nuts and did the same thing. So I'm going to edit this and put my data in. And my data had 240, the number of peanuts in my sample, and 357 was the total number of whole nuts to the best of my ability to estimate that. And if I generate sampling, so that was about 67% of the nuts were peanuts. That seems far from 50 to me. Let's see. So here notice the StatKey scroll, there we go. The 67.3, I'm doing a confidence interval. In a confidence interval, it's the sample that ends up at the bottom. Hypothesis test, it's the null that ends up at the bottom. So those are two slightly different ideas, but this is still a symmetric bell-shaped curve. So my point is, it doesn't seem to matter where I get my data from. If I'm looking at a mean or a proportion, and I run a simulated sampling distribution of it, it seems to be the symmetric bell-shaped curve all the time. It's ubiquitous. So this was proportion of peanuts. And I had n equals 357 to the best estimate I had. Restaurant tips, n was 157. And still I get this symmetric bell-shaped curve here. And so this is again another part of the central limit theorem, which we're going to be exploring for the next few weeks, which is related to everything we've been doing. So more on the central limit theorem. So in addition to saying the mean of the sample should be about the same as the mean as the population, so that's one thing the central limit theorem says. Mean of sample should be about the same as the mean of the population. To the sampling distribution should be a symmetric bell shape more specific than that, called a normal distribution. So that shape we kept coming up with is a normal distribution. Normal distribution came up way back in chapter 2 with this idea called the empirical rule. I'll remind you of, so normal distribution, distribution, the idea called the empirical rule. What the empirical rule says is in this symmetric bell shape we call a normal distribution. We have our mean right in the middle of it. It's symmetric. And then if we look one standard deviation on each side, so go one standard deviation to the left, go one standard deviation to the right, then in this range right here, we would expect to find about 68% of the data. If we look two standard deviations on each side, does anybody remember that one?
It's 95%.
Yeah, so that one's the 95%. So I'd expect to find about 95%. And the empirical rule goes on to state 3 standard deviations. So if we were to jump 3 standard deviations on each side, so -3 on that side, +3 on that side, in this range right here, we would expect to find about 99.7% of the data in between there. So if something is normally distributed, then these are what we expect the spread of the graph to look like. If that is the spread, it's a symmetric bell shape, then we say, okay, this is a normal distribution. And sampling distributions tend to be normal for means, for proportions, not for everything, but those are the things we're looking at right now. What else? For correlation coefficient, for slope, on a graph like we were finding before, and then difference in means and difference in proportions we'll talk more about later. But there's a lot of things that this pops up for. And so many of the examples, regardless of where the data came from, when we ran the sampling distribution, we got this symmetric bell shape. So it turns out a normal distribution actually has an equation, and depending on other math classes you have, you might have seen the equation before, but most likely not. We're not going to look at the equation itself, but we are going to use technology to get values from this. So